So finally here we've been talking about the concept of correlation, but I want to start putting some numbers to it and look at how to actually calculate it and also how to determine significance, okay? Here are some general descriptors that we've been using, like strong positive or moderate and those kinds of things. And our book even gives us some general guidelines as to what really defines a strong or very strong or moderate. But the fact of the matter is, we can't really say whether these things are significant unless we consider a few other things. One of those being, how many data points are we getting? Okay? Because I could say, hey, I got an R value, I got my Pearson's R value to equal 0.8. Now that falls in this moderate positive. Okay? Does that mean it's significant? Well, it really depends. If we use n for the number of data points we have. If I only had, 6 people that I was getting data from, and there was only a 0.8 correlation, that's not really that great. Okay? If I had 60 people and had a 0.8 as my correlation coefficient, that would be significant at that point, because I'm getting lots of data, and even with lots of that data, I'm getting that strong of a correlation. It is actually significant. In fact, we can even have some values that are down in this weak range, and if we have enough data to give us that, it can still be statistically significant. All right? So, yes?
Why is there so much of a gap for the moderate? Because like for strong and very strong, it really only is 0.13 like for both of them.
Part of it has to do, you'll see later, we're going to look at what's called a critical value table. Okay? And by the way, I'm showing you one way of interpreting these. There are other ways where you can use R values and then do t-tests and stuff with that kind of in combination. If you're doing AP stats, you would do it kind of that way. I'm showing you a way that can be used. It's not quite as involved as what they're doing in AP stats. It's a little simpler just to establish. But again, these are just general windows, okay? And it's kind of like it's getting smaller, because to qualify, it's a smaller part of that is very strong. And then to qualify as strong, it's a little bit broader. It's almost like the bell curve kind of thing. The real high levels are very small numbers that fall into that. But as you'll see later, we've got a better way to do it than just by using these guidelines. Okay? So, in order to do this, one of the things that we're going to be doing is the hypothesis test. Okay? You may have done some hypothesis tests in science class or something like that, but I want to discuss this because I actually want you to be able to do some hypothesis testing for data that we have. Okay? So there's kind of 5 parts to a hypothesis test that we're going to look at. The first thing that you need to do is state a null hypothesis. When we are testing for correlation, we are always going to hypothesize, first of all, that there is no correlation. Okay? And you're actually going to write it out that way and say there, H sub naught, there is no correlation between this and this. You need to put it in context of the problem. Okay? Then you're going to state an alternative hypothesis. The alternative is the opposite. Okay? It's pretty easy. If the alternative to there being no correlation is that there is correlation. And what we're talking about here, when we talk about correlation here, we're talking about statistically significant. Now, how do we define significant? That's down here actually. We're going to use a 0.05 level of significance for what we're doing. That means we are 95% confident that if we find a correlation, it's not the result of just some goofy data or just the result of chance. Okay? If we find a correlation, we're 95% certain that there actually is a relationship going on here. Okay? So that's what we mean by statistically significant. Depending on the study you're doing, you could use a 0.1, so we're 90% confident. Or if you want to be really sure, you could use a 0.01. Alright, so you're 99% confident. Alright, and obviously, depending on the situation, you may want, if I'm testing out a new medicine, a 5% room for error isn't quite good enough for me if I'm taking the medicine. Okay, I'd want them to be a little more sure than that. Okay, the next thing is we're going to calculate Pearson's R, and that's what we're going to do here in just a moment. We'll look at the formula, and then comes the interpretation here. Once you get that R value, is it significant or not? So we have, first of all, what's known as degrees of freedom. All right, degrees of freedom. And for Pearson's R, it's always going to be n minus 2. Okay? It's always going to be n minus 2. So if you have 6 pieces of data, you're going to have 4 degrees of freedom. If you have 100 pieces of data, you're going to have 98 degrees of freedom. All right? That's going to help us decide what value to choose out of our critical value table. You'll notice I'm mentioning a table here. We'll see that later. This is the critical value table. Okay? Now, that critical value that we find using the degrees of freedom is going to tell us the minimum value for R in order to reject our null hypothesis. Okay? So when we look on the table and we see a point, 682, our R value has to be at least that in order for us to say we're going to reject the null hypothesis, therefore we're going to accept that there must be a correlation. Okay?
So where does R fit in that correlation? Sorry. How do you get R from it?
Well, I'm glad you asked. Here we go. Okay?
Oh, wow.
Here's a formula. All right? Let's check out this formula here. It's actually a little simpler than it seems as long as you stay organized.
That was so perfect.
Okay? Yeah,
Good job,
I have a plant, to ask the key questions. So if we look at our formula here, I want to examine a few things. All right? Those are sigmas, if you can't tell from my handwriting. Those are sigmas, so we have a number of sums. The scores that we're talking about are the x's and y's. All right? So we have x's and y's that are paired up. So we have the point 4, 4, 5, 6, 3, 5, 6, 7, and 10, 7. All right? Now, these variables could represent anything. Okay? In first period we were talking about, we've got a number of football fans in first period, so they were saying, what if X was the number of rushes by a running back, and then Y was the number of yards gained? Okay? We could see, hey, does an increase in the number of rushes you get translate into more yards. Now, this would be a lousy game. When they hand the ball off to the running back and he tries to run for yardage in football.
American. Okay,
Yeah, in American football.
American.
American football, yeah.
Yeah.
I only know big time.
So they hand it off to the guy and he tries to run as far as he can.
So the
with
number
our-
of times he tries to run?
Yes,
Okay.
that would be
Does it still count
the
if he
rushes.
gets tackled?
Yeah, yeah.
Okay.
So he's rushing, he runs it 4 times and he only gets 4 yards. That would be a terrible game.
Like
Okay.
for all 4 or like 4
Total,
per-
total
That's
yards.
like
This was the best we could come up with, so. The situation doesn't really matter, but I want to have some kind of a situation for our hypothesis test. Okay? That's the best thing I could come up with in, 20 seconds. So here's what we have, okay? Notice in the formula, we have a few different things. We have n showing up a couple of times, all right? N is our number of scores. So in this case, how many do we have?
5.
We've got 5, okay? So n is going to equal 5 in this case. All of these are sums, but pay attention to what they're the sums of, okay? Here, we're multiplying all the x's and y's together and then adding up those products, okay? So you'll notice I put my data into a little table. Okay, so I have my x's, I have my y's, and now we're going to multiply all those together. So 4 times 4 would be 16, 5 times 6 is 30, 3 times 5 is 15, 42, and 70. And then we add those all up, okay, so that's 160, 73. That's what's going to go in the formula right there. Okay? Does that make sense?
So 5 times 173?
Yeah, that's going to be the first part here in our formula. It would be 5 times 173. Okay? Now, our next part of the formula, we have the sum of all the x's times the sum of all the y's. Okay? And I actually already did this part here. If we add up all of the x's, we get 28. We add up all the y's, we get 29. Okay? So at this point, I actually can go ahead and start calculating r with my numerator. I'm going to have 5 times 173, like Kate said, minus the sum of the x's, 28, times the sum of the y's, 29. Okay? So that's not too bad yet, right? Alright, so what does our numerator end up giving us? We haven't done the denominator yet, but we'll get there. What's our numerator? Five times 173 minus 28 times 29. What? 53. Okay? So there's our numerator. So now we start looking at the denominator. The denominator can get a little messy, so you got to be real careful with it. Okay? There's a big square root over the entire thing. And then there's 2 sets of brackets inside of it. Okay? Now notice here, we have n again. So that's 5 times something. Alright? So we're multiplying n by the sum of the x squareds. Notice here I'm squaring the x's first, then I'm adding them up. So that's why I have this column in my table. 4 squared is 16, then 25, 9, 36, and 100. Okay? So we get 186. So that's what I'm going to substitute in here. 5 times 186 minus, now notice here, this is not the same thing that we just used. This is the sum of the x's squared. So what are we squaring here?
The 28.
The 28. There you go. So it's 5 times 186 minus 28 squared.
28's in parentheses, right?
It's inside the parentheses there with the rest of it.
No,
So
I'm just saying, it would be, like, just because the subtraction sign, it's like, would you do 28 first and then?
yeah, you do 28, square it, and then we're subtracting. So what does this first set of parentheses come out to? 5 times 186 minus 28 squared.
146.
146. Okay. So now let's look at the second set of parentheses. It says, what?
Sorry, really quickly. So the one, the second parentheses, would you do y squared first and then the sum of that?
Yes, that's why we have this column right here. We're going to square all the y's and then add them up. Okay? So the y squareds are going to be 16, 36, 25, 49, and 49. Okay? So that's going to be 175. Okay? So now we're plugging that in. N times the sum of the y squareds minus the sum of the y's squared. So 29 squared. And what do we get there?
34.
34?
Yeah.
Okay. So now we have something a little bit more manageable that we can plug into our calculator. So at this point, what do we end up getting for r? 53 divided by the square root of 146 times 34.
0.75.
0.75? Let's do 3 sig figs, so it would be 7.5 what?
752.
Okay, good. 0.752.
So it's not reliable?
Well, we don't know. We don't know. We need to determine significance, okay? Now, here's where our hypothesis test comes in, okay? We were talking about the number of rushes and the number of yards. So, what would our hypothesis, our null hypothesis for this be?
They don't have a correlation.
Okay, so we would write out there is no correlation, I'm going to abbreviate a little bit, between the number of rushes that a running back has and the number of yards that he gains. Okay? So what would H sub 1 be? What's the alternative to that?
There will be correlation.
There is a correlation between number of rushes and number of yards, okay? And I know it kind of seems silly to write this out, but it's important for our hypothesis test that you lay out both the possibilities.
But how do we know that there is no zero, H0, but there is H1?
Well, no, those are, a hypothesis is an educated guess based on, trying to predict what's going to happen, all right? So we're predicting, our initial hypothesis that we're testing is that there is no correlation. If we prove if we are able to reject that, then we would automatically accept the alternative, and the alternative is
So if
this.
R is not 0, then it's not H0, right?
If, no. If it doesn't turn out, as you'll see, if it doesn't turn out in the region where we can reject it, then we would accept it and say, no, there's no significant correlation here. Okay? Let's keep working through it, and I think it'll make sense as we go, as we flesh this out. What's our degrees of freedom going to be? How do we find degrees of freedom?
Was the
N minus 2, right?
So it's
So we'd have 3. Now, let me just show you this real fast, okay? We come back here, and we say, okay, the region of rejection is any R that's greater than or equal to 0.878. However, 0.752 is not greater than 0.878. Therefore, we accept, we cannot reject H sub naught. We're going to accept H sub naught, that there is no significant correlation. And we would flesh that out, but because of time, I'll let you guys go.
Could you go back to
Okay.
the other slide a second? The rejection. Wait, how do we know what N is again?
It's the number of values. We had 5. So here, degrees of freedom, level of significance. For 3 degrees of freedom, we need a 0.878.
So yes, it is significant.
So